Today we're going to cover statistics vocabulary and hypothesis testing. Today's objectives are to cover some of the things that we went over in our last lecture, and we're going to go over background to statistical testing and hypothesis testing, and you're also going to get an introduction to what inferential statistics is. We will cover qualitative versus quantitative data, and also alpha values, and as that relates to type 1 and type 2 errors in research. Some of these things we've already covered, starting with what a variable is. So a variable is just a single aspect or characteristic that's associated with the individuals under consideration. And in the last lecture, we also talked about independent variables and dependent variables. Again, the independent variable is the variable that's thought to cause a change in the dependent variable, and the dependent variable is then the outcome. So when we do statistics, what we're doing is we want to make an inference based on the sample that we have onto a certain population. So the population is the set of data corresponding to an entire group. So for example, if our population was all college students in the state of Massachusetts, realistically, we'd never be able to conduct a study that looked at all college students in the state of Massachusetts, which is why we have a sample. So the sample is the subset of the population that's at where data is actually collected. So for example, we might study 35 students from UMass Boston and then make an inference from that information onto all college students in the state of Massachusetts. From a population, we get a parameter. So a parameter is a characteristic of the population. So for example, the average VO2 max of all females aged 18 to 25 in Massachusetts. Again, we can't run a test studying all of these individuals, so we need a sample. And this is where we get a statistic. So a statistic is a characteristic of the sample. So that might be the average VO2 max, so aerobic capacity of 35 females from UMass Boston. And from that information, we would make inferences from the sample onto the population. This might be a graph or a variation of a graph that you've seen before, where we're looking at adults who have obesity. So here's the national average, and you see that it's 30%. But of course, researchers in this study didn't measure every single person in the United States. What they did is they took a sample, and then they made an inference onto the population. So that was some background on statistical testing, some things that we've already talked about. We'll get more into hypothesis testing, but that was inferential statistics. We're taking information from a sample and applying it to the population. So next, some of this might be familiar as well, but it's qualitative versus quantitative data. So quantitative data involves assessing the quantity of something using a numerical value. So this might be how fast a person runs a 40-yard dash. It's really how much of something. Qualitative data involves assessing the quality of something, and we do that using a non-numerical value. So that might ask someone how they feel. So for example, if someone runs a 40-yard dash, we get a time that's quantitative. If we ask them how they feel after it, that would be qualitative data. So if we look at an RPE scale, sometimes it's measured up to 20, from 6 to 20, but in this case I just use a 1 to 10. This is qualitative data. So we might ask someone how they feel when they're exercising, and then rank them. So where 0 means they're resting, and 10 means the hardest you could possibly work. Quantitative data might involve measuring how much muscle somebody gained after a program. Qualitative variables, and these are some terms we went over in a previous lecture, they can be categorical. So an individual can fall into one of a number of categories, but the categories don't have a natural order. So for example, male and female don't have a natural order. The source of a leg injury where it hurts, hamstrings, quadriceps, it doesn't have a natural order. Categorical, so nominal data, puts people into bins. Qualitative variables can also be ordered. So that's ordinal variables. An individual might fall into any number of categories that actually have a natural order. So for example, back pain. we know that worst possible pain, which might be represented with a 10, is worse than moderate pain. So it does have a natural order, but it's still describing things. Quantitative variables, on the other hand, are usually continuous variables, and they can take on any value across a wide range. In its simplest form, this information can go from 0 to infinity. That's not saying that that's what you'll see, but it's possible. So height and weight are examples of this. You might ask somebody how much they bench press. That would be another example of that. It can go from 0 anywhere up to a relatively large number. Now we'll compare categorical data to continuous data. In general, variables either represent measurements on a continuous scale or they represent information about the same categorical characteristics. So we talked about that. Continuous data might be height, weight, distance ran, speed, or velocity. And categorical data might include things such as gender, occupation, or marital status. And again, this is from our last lecture. We might categorize people as high fit, moderate fit, or low fit. Again, think of this as people can fit into specific bins here. You can't be high fit and also low fit at the same time. There's different levels of variables, so these are ways to quantify categorical data. An example would be, how many classes are there at UMass Boston? How many different levels? Well, there's going to be 5 levels, so you could be freshman, sophomore, junior, senior, or you could be a graduate student. We're going to move into hypothesis testing. So with hypothesis testing, again, the goal is to make a statement or statistical decision regarding unknown popular parameter values based on sample data. So again, we're taking a sample and making an inference onto the population. With hypothesis testing, we have what's called null and also alternative hypotheses. The one that you're probably most familiar with is an alternative hypothesis. Each research question will have a null and an alternative hypothesis. Null hypotheses are symbolized as an H with a 0 next to it, and it states the situation in which there is no difference or relationship between populations. So in this case, the difference or the relationship is null, as in it doesn't exist. Alternative hypotheses are the opposite of null hypotheses, and it's symbolized as HA. This is what you probably often see in research papers. It's identified as the research hypothesis or the hunch that the investigator wants to test. We'll move on to alpha values now. If you've read a research paper, you might have seen something like this. A little p, and then a value that's often 0.05. So what does that mean? This information will help us decide when we retain or when we reject a null hypothesis. And we'll get into alpha values more so it makes sense. So if p is 0.05 or less, we would reject a null hypothesis. So we reject a null hypothesis if the sample mean is so deviant that the probability of occurrence in random sampling is less than that alpha level. In other words, we would accept our research hypothesis if alpha is 0.05 or less. This criterion is called the level of significance, and it's often symbolized as alpha. Alpha or p-values represent the probability of making a type 1 error. When you see this term 0.05, this means that there's a 5% chance probability of getting the data we have if no effect actually exists. It's not special in any way and can change based on the research question, but 0.05 is commonly used. We might see lower numbers, for example, in medical research where they are testing medicine and they don't want to leave things up to chance. Let's take a funny example. Let's take Sue. Sue believes that rubbing a cat on her head is a great cure for headaches, so she wants to conduct a study. Her hypothesis, or her alternative hypothesis, is that rubbing a cat on her head will cure headaches. So therefore, what the null hypothesis has to be is that there's no relationship in headache symptoms between people who do rub a cat on their head and people who don't rub a cat on their head. Sue decides to set her alpha level at 0.05 and then goes to work conducting a research study. So again, Sue conducts a study. Her null is that there's no difference. There's no difference between people who rub a cat on their head and those who don't for headache symptoms. The probability of making an error is set by alpha. So let's say that Sue runs a study and she actually finds a difference. So she finds that people who rub cats on their head reduce their headache symptoms compared to people that don't rub a cat on their head. Because she saw a difference, she rejects her null hypothesis, which is of course an error because she probably got there by random chance. In this case, Sue is either right that rubbing a cat on her head reduces headache symptoms, or she committed a type 1 error. Now let's say that Sue ran this study 20 times. Statistically speaking, she might find a result in one of those studies just by random chance. So if this was the case where she did find a result just by random chance, and the truth was, which we would probably agree, that there is no difference in all of these other studies right here, Sue might not find a difference. But because she did find a difference in this one study, when the truth is that there is no difference, she's probably committing what's called a type 1 error. And we'll get into that more. Now, if Sue had set a lower alpha, then she might not have found statistical significance. Okay? So if you set a lower alpha, such as 0.01, a couple of things happen. One, it's harder to prove your statistics are actually true. But you have a much smaller chance that your conclusion is false. In general, in research, you won't see alpha levels any higher than 0.05. In exercise and health science research, this is generally what people use is 0.05, but you might also see 0.01. Here's another example. Let's say that you make a research hypothesis. There are differences in between height between men and women. Your null hypothesis would be that there's no difference in height between men and women. And your alternative hypothesis would be that there is a relationship between men's height and women's height. Whenever you have a hypothesis, there's 4 possibilities. The first is that you would reject a true hypothesis. The second is that you may fail to reject a true hypothesis. You might reject a false hypothesis, or you might fail to reject a false hypothesis. In research, if the null hypothesis is correct, we fail to reject the null hypothesis. As a researcher, you don't want that to happen because that means that you were wrong. If the alternative hypothesis is correct, we reject the null hypothesis. And if you're conducting research, this is what we want to happen because it means that your hypothesis is correct. You've already been slightly introduced to type 1 and you've been introduced to type 1 errors. There's also another kind of error called a type 2 error. A type 1 error can also be considered basically a false positive. So where there's no results, but the test shows that there are results. A type 2 error is a false negative when the person actually has a condition and the test says that they don't. If you were in a rehabilitation setting, you might do a shoulder impingement test, such as the one right here. Again, let's say that you're conducting this shoulder impingement test. Again, there's 4 possibilities to deal with a hypothesis. You might reject a true hypothesis. You might fail to reject a true hypothesis. You might reject a false hypothesis. And you might fail to reject a false hypothesis. So let's say that the person actually does have shoulder impingement, and the test comes out positive for shoulder impingement. That's a good conclusion. But let's say that the person does not have shoulder impingement, or let's say that the person does not have shoulder impingement and the test says that you don't have shoulder impingement. That's good as well. But let's say that somebody does have shoulder impingement, but the test does not show that they have shoulder impingement. That's not going to be good. And let's say that somebody doesn't have shoulder impingement, but a test says that they have shoulder impingement. Again, that's not necessarily going to be good. So type 1 error is a false positive. It's asserting something as true when it's actually false. So think back to Sue, who asserts that rubbing cats on her head cures headaches when it's actually false. That is a type 1 error. Let's use an exercise science example. Let's say that you wanted to understand the difference in muscle growth when someone trains with barbells versus when they train with dumbbells. Maybe you believe that training with barbells leads to greater muscle growth. But your null hypothesis in that case would be there is no difference between training with dumbbells and barbells on muscle growth, and we'll throw in using the same exact load. If we reject the null hypothesis, that means there is a relationship. In other words, you'd be accepting your research hypothesis. The probability of making an error is going to be set by the alpha level. So your two groups, you have 200 people in both groups, and they both do 3 sets of 10 with 100 pounds. And your first group gains 3.2 pounds of muscle, and your second group gains 3 pounds of muscle. So you look at that, and without necessarily looking at a p-value, you might think the barbell group gained more muscle, and you might say the barbell group is the best group, and you want to go out and tell people that they should be training with barbells because that leads to greater muscle growth. So in this case, you would have rejected the null hypothesis. So when you rejected the true null hypothesis. Your null was that there was no difference. You observed a difference, so you rejected the null. In this case, you were either correct or you committed what's called a type 1 error, which is a false positive. So even if you did see a difference, you still have a 5% chance of being wrong with an alpha level of 0.05. So once again, in this case, you might have done the one study where by chance the barbell group gained more muscle. And this is just the risk that you take whenever you conduct research. So the rejection again means that there is a relationship. So we're saying that, or there is a relationship or there is a difference. In this case, we're saying that barbells might be more effective than dumbbells based on the alpha level that we set as a researcher. Once again, if you rejected the null, you know that you were either right or you made a type 1 error. Contrary to that, if you accepted a null hypothesis, you know that you're either right or you made a type 2 error. Now let's talk about a different study. Let's say that there's no difference in muscle mass between training with 3 sets and training with 5 sets. In this case, we're using the same training modality, barbells, but group 1 trains with 5 sets and group 2 trains with 3 sets. In this case, I intentionally made the sample size smaller so that you could understand how type 2 errors might be made. So group 1 goes through your training protocol and they gain 2.95 pounds of muscle, and group 2 gains 2.75 pounds of muscle. So you want to see if the difference between these two groups is significant. So this is our output, and I'll show you how that's done. So if we looked at our data, we could see that we have groups that are denoted by 0 or 1, and there's 10 participants in each group, and we measured how much muscle that these participants gained, and then we want to compare the differences. So if we went back to our output, You can do this in a number of different ways. We can go statistics. You actually will eventually be doing this test. It's a t-test. So what we might end up doing is when we would type in t-test, muscle gain. So this is one of our variables right here, muscle gain. And then we want the difference to be by group, so by group status. And this is the output that we get. So if we go back to our lecture, we can see that the p-value that we got was actually higher than 0.05. It's 0.32. And if you can see right here, we have a mean of 2.95 for the first group, and then for the second group, we have a mean of 2.75. But according to this, there are no significant differences between the two groups because our p-value was higher than 0.05. So we would have to accept this null hypothesis that there is no difference. Now, that might be accepting a false null hypothesis. So maybe there actually is a relationship. So again, our null was there's no relationship between sets and muscle growth, and we had to accept that. Now, this is denoted by beta, which you don't necessarily need to know right now, but that's completely dictated by the sample size and the variability within the sample size. So if there actually was a difference and we accepted the null hypothesis, we have a false negative. So our alternative hypothesis, which might have been lifting with 5 sets compared to 3 sets, would result in greater muscle growth, but we didn't actually find that, so we would have to reject our alternative hypothesis and accept our null. So in this case, with a type 2 error, you say that there's not a relationship between sets completed and muscle mass, when in truth there actually is. And you might commit a type 2 error for any number of reasons. So one might be lack of sufficient power, which means that the sample size is too small. If we found the results of 2.75 versus 2.95 in a large sample, so for example the 200 and 200 in each group, our statistics might show that there is a significant difference. But because we had such a small sample size, we might not have observed significance. There might also be issues in measurement error, or a treatment was not properly applied. So if my group was not actually my 5-set group, maybe if they did 4 sets instead, then the treatment wasn't properly applied. Or if my alpha level was too conservative, which in this case it probably wasn't. Type 1 errors might also be caused by measurement errors. They might be caused by a lack of random sampling. Alpha level might actually be too liberal, so a high alpha level. Investigator bias, or improper use of one-tailed tests, which we'll discuss later. So understanding the relationship between alpha and the p-value is going to be incredibly important for the remainder of this class. It's going to be used to determine statistical significance for all of the tests that we cover. So let's run through a couple practical examples so that you can get a better handle on this. And we'll use correlation. So it's just looking at the relationship between two variables. So if we had a research question that was, are daily steps taken and caloric burn related? Our research hypothesis or our alternative hypothesis would be that there is a relationship between daily steps taken and then caloric burn. If we wanted to know the null, we just flip this around and we say there is no relationship between daily steps taken and caloric burn. Now let's say that we ran a correlation and we see that we see this value, and it's 0.896. So this is just saying the relationship between steps taken and calories burned. Now, this is pretty close to 1, so it's a strong and positive correlation. Then what we look at right here is our p-value. Because this value is less than 0.05, we say that the results are significant. And this basically right here just shows that you're always going to find a perfect correlation between the same exact variable. The relationship between steps and steps is always going to be 1. And again, we see 0.89 as a strong and positive relationship, which is also significant between calories burned and steps taken. So again, our null hypothesis is that there is no relationship between daily steps taken and caloric burn. But because my test came out to show significance, I need to reject my null hypothesis. I observed a relationship, so I rejected the null. In this case, I was either right or I committed a type 1 error. Now, most of the time in research, you will not read a paper and see someone talking about a null hypothesis. So we don't get caught up in talking about null hypotheses. We make best guesses based on relationships. So let's say in another example that I believe that a person who believes in the positive outcomes of resistance training would also have a greater intention to engage in resistance training. That is, intention and it's called outcome expectancy are related. I would make a hypothesis that there's a positive correlation between perceived positive outcomes and then intention to do resistance training. The null hypothesis would then be that there is no relationship. Now in Stata, so I'll pull this up as well, you would run a correlation. All right, here's our data set. And if we look at here, we have outcome expectation, and then we also have intention. So what I would do is I would do PW, you can do core or PW core. And then we want to do intention. And then what we can do is just double click on this. And because we want to know if something is significant, we just have to add comma and then sig. So now what we have is a value of 0.51, which is positive and moderately strong. And we also see that our p-value is 0.0002, which is less than 0.05. So because of this, we would say that there is a significant relationship between intention to do resistance training and then outcome expectation. So we're saying that the relationship really did exist, which is great for a research hypothesis. Therefore, we need to reject the null. But let's say that the relationship really did exist and I didn't observe it. So let's say that this number was 0.1. So the relationship really does exist, but it was not observed. Because it was observed, I would have to accept my null hypothesis, which in reality I would be wrong and committing a type 2 error.